Okay, I think we'll get started. Thank you all for joining us this morning for Elena Glassman's thesis defense. My name is Rob Miller. I'm Elena's advisor. Some of the best theses, I think, are inspired by personal experience, and that's certainly true for Elena's thesis. I hope she'll tell us actually a little bit about her experience as a TA that inspired this work, but she's generalized from that to think about a problem that is of great importance to teachers of MOOCs, which is how do you figure out what your thousands of students are actually doing, what they're actually submitting for their programming assignments. Let me say a bit about the way that this session will go. Elena will talk for hopefully about 45 minutes, and then the first questions will come from her committee, which is me and Leslie Cabling on the remote, on the Hangout, and Chris Turman, who is here. Cool. And then we'll open up to questions from the audience. And once we've exhausted all of that, we'll kick everybody out, including Elena, and the committee will have a private chat, and then we'll invite Elena back to grill her. But hopefully a little bit after that, you'll find out the result. So with no further ado, Elena, take it away.
Okay, hi everyone. I'm going to be talking about massive programming classes, as Rob has just said. There's a lot of them out there. You don't have to go to Coursera or edX to get thousands of students, or either in one semester or over several, okay, who are completing your programming exercises that you're assigning several of which every week. And learning how to program is becoming both a career, financially rewarding, ever since the first software developers, say like Margaret Hamilton at NASA. And it's also personally empowering because we all have computers sitting in our pocket. Well, many people have computers sitting in their pockets. For example, these high school students are trying to write apps and design businesses around writing code that improves the lives of their community members in and around Jerusalem. So this is, there's a lot of reasons to learn how to code. So we have big classes. Here are some examples of problems and the types of solutions that students are asked to write several times per week in these classes, like exponentiating a number, computing a derivative, approximating a logarithm. Okay? These are small functions, but for beginning programmers, this is the kind of material you're working with. Now, if you think about my thesis title, Clustering and Visualizing Solution Variation, you're probably imagining something like this. Okay? This is exactly what we're not doing. Okay? This could be thousands of students going through some process to get to a correct solution. This could be a network of thousands of solutions and whether or not they're within a threshold of closeness to each other. It's not really clear. Okay, and this is not actually, this is more like Jackson Pollock. It's kind of just to make you impressed with the underlying code base. This was done by Huang et al. At Stanford. Okay, but the problem is how, if you gave this to a teacher, how would they even know what that rightmost cluster meant, right? If this is a network of solutions and whether or not they're close to each other, it's hard to really infer what the true variation in your student solutions, all the different ways that they solved it just by looking at this. So the first idea that I'm going to present of several in this thesis defense is how to cluster and visualize solutions in a human readable way, so that you can say, oh, I can read this single solution, and it represents a cluster of 1,538 solutions, okay, in some sort of deterministic, interpretable way. Okay, so for the rest of this talk, first I'm going to tell you about the remaining part of my title I haven't explained yet, which is what I mean by solution variation. And then I'm going to go through 4 research questions. How do we understand, how do we make it cognitively available, like what it means to have solution variation in thousands of solutions? How to give feedback on this variation at scale, how to personalize that feedback, and finally, whether or not systems that can collect and distribute student advice, given that there's so many different ways to solve the problem. Finally, we'll discuss things really fast and play with future work. All right, so many ways to describe solution variation, but there's 3. There's a taxonomy here of correctness, approach, and readability that I find very helpful. Correctness, it's very hard to prove for arbitrary code that it's just correct. So we approximate correctness with test cases, both in industry and in education. The teacher sets out a set of inputs and expected outputs. If the student's code meets those expectations, it's considered correct. And this can be automated with an autograder. The teacher can set this up, walk away, and for years to come, students can come to this exercise and benefit from trying to write a solution that passes all the test cases. Autograders can only do so much though. So these are all correct, and yet they're vastly different. The top left is exponentiates a base in an iterative way. The bottom left is recursive, it's calling itself. And the one on the right, that one's just unreadable. But it is correct. So I don't want my autograder to let this all pass. Okay. Now let's break down what I mean by approach. There's many different ways that you can approach solving a problem. One is to use the internal library of Python. Okay. You just you subverted the teacher's intentions with that one because they want you to write iteration. They want you to exponentiate basically exponent. This next one is correct. Okay, but I've included this keyword. The comment here to indicate that continue keyword is being included when it doesn't change the operation of the program at all. Maybe someone has a broken model of what while does. We want to call that out, even though it's not incorrect. It just reveals a possible exception. Another thing to think about when we have these multiple approaches for problems is that there's a distribution of solutions that students take on. So if you think of your collective set of students as this generator function, okay, that is generating these distributions over solutions, I want to know the common ones and the uncommon ones. The unusual ones could be bad. They could be super innovative. Just 3-sentence story to illustrate this from my own teaching experience. We had a student, all the 200 students were writing code to specify these little processors, okay? And one student said, I've got an optimization. No one's talked about this before. He codes it up, he puts it up on the class forum for everyone else to see. And rather than punishing him, we're like, wow, that's a really cool thing. We've never seen that before, and we helped everyone else write that solution. Now, that student understood that their new way of thinking about the problem was innovative. But not every student does. Many students, when I'm talking to them at the end of their lab, they say, am I normal? Did everyone else do it this way, right? I want to be able to help recognize students' innovation, not wait for them to tell me that they came up with something new. Finally, there's readability. So again, this is the same very difficult to read code. It's kind of like the programming equivalent of this, right? This sentence, incomplete implementation of strategized programmatics design, may be semantically meaningful, but it is inscrutable, right? And so these two things are to be avoided. Languages, whether they're written to be interpreted by computers or by humans, at the end of the day, they're still all to be interpreted by humans. So readability matters. You can't commit to the Google code base without having some person look over your shoulder and says, looks good to me, right? That's not something we've automated. And yet we don't really give feedback in a systematic way to our programming students. In fact, a lot of people now taking our introductory programming classes, it's the first and last programming class they'll ever take because it's becoming a requirement for all the other majors as well. It's like a general institute requirement. So we can't wait for these bad practices to be beaten out of them in subsequent courses. If they're going to walk back to their biology lab and write a script that processes the output of their machines, right? Hopefully they're reading code that they can read again next month, next year, or for the poor soul who has to read their code the year later after they graduated. So readability matters. Also, I just want to point out, for anyone who wants to push back on this idea that readability matters in introductory Python programming classes, unreadable code is a cause of and a symptom of confusion. So I'll just put that there. Now, student design choices, like whether they use a for or a while, whether they use syntactic sugar, whether they use recursion or iteration, these all affect correctness, approach, and readability. And that's what I mean when I talk about, these are the things that result in solution variation that I then try to analyze. Okay. To reduce the cognitive load on teachers who are looking at all this code, I just want to point out, this is foreshadowing for later, that these two solutions are exactly the same, except they have different comments, different statement order, and different variable names. It's very difficult for you to just look at that and be like, oh yeah, of course I did that. Okay. The second person may be from Poland because Winnick is result in Polish. We did see that in our data set, so people do use many different languages. So if you're a college level teacher of programming, you may very well have a folder on your hard drive that looks like this, which is just piles of student implementations in their raw form to the same solution, right? And so if you're stepping through and they all differ in all these interesting but some important, some not important ways, it's difficult to really understand. So one moment, please. I'm just going to plug in and plug out, or plug out and plug in. Is everyone? You know what? This probably turned off. It does that. Can someone hit the button that turns it on? Here.
Laptop 1. It does appear to be laptop 1.
Laptop 1? There we go. It's coming back.
It is?
This is why you test the same room that you actually do your defense in.
It's coming back. Oh. This looks like a broken pole.
How long has it been on? Sorry. What is this timeout?
It's timeout. I think it's about an hour.
That's terrible.
Yeah, it is. Here we go. All right, so what I've described to you is both a challenge and an opportunity. The challenge is to actually cognitively understand what students wrote and to give feedback at scale. And the opportunity is that there may be, when you have so many students, a dense enough sampling of these solution spaces that we can really derive new value. Okay, more specifically, the opportunity I'm trying to take advantage of is exploiting solution variation within these large data sets. So teachers could learn about new solutions from students, right, that they didn't know about before. Find better examples for discussion. Wouldn't it be great to walk into the class the next day after assignment was due and say, hey guys, I saw there's several interesting ways that you solved this. Let's talk about when to use one over the other, because engineering is all about trade-offs and finding the right solution at the right, for the right context. Or also, here's some ways you really don't want to do it that I observed in your code. So that's what I think would be a great teaching experience for students and teachers. Also, teachers could potentially use this exploit solution variation to write better feedback that's more appropriate, more tailored. Write better test cases. So if you're exposing test cases or corner cases that are not being caught by your test case suite, this is a place to discover it. And also write better evaluation metrics if you're sitting down for a whole day and grading by hand. Finally, if there's solution variation, students can be tapped to be the experts on their particular solutions that they implemented, particular bugs that they fixed, right? So taking advantage of that local expertise. Okay, so I'm going to just illustrate this with one more personal story from my own teaching experience. I think captures a lot of these pieces. We asked students to write code that described in a simulated fashion what this is. This is a Turing machine. It's an abstract model of computation. Someone made it fairly concrete for you here. It's reading and writing from a tape and moving that tape along. Okay, so during its computation of on this tape, the tape moves. And when I was having trouble helping people in a class of 200 all debug their simulated Turing machines, okay, I went back after the semester was over, and I plotted the movement of all the Turing machine heads on a single test tape. And I was able to, by hand, see that the motion of the tape for a significant portion of students, here on the left, for 50%, followed a particular pattern that indicated one strategy, and a second pattern that was distinct from that was using a different strategy. So already I knew that 90% of the students were doing one of two mutually exclusive strategies, that if I walked in the lab the next day, I could hopefully recognize one or the other as I'm debugging with students. I also want to point out that among the 10% that were of more unusual design, 2 of them passed all the test cases but subverted, again, the teacher instructions. So fellow teachers were not all aware that there were multiple solutions. And in fact, one teacher said, oh gosh, I might have, whenever I came to a student who was working on a solution with a strategy I didn't recognize, I often, if they were struggling, I said, I don't know that that works. Do it my way, right? And we want to avoid that as much as possible. So this can be, this is a small example of what I'm trying to make more general. Okay, research questions. You can't read all the solutions at once. Can't maybe ever read them all. So how do you understand the common and uncommon variation? How do you give feedback on approach and readability, these things that we don't have automated tools for? these first 7 of 3,800 solutions to this exponentiation based on the exponent, and tell me what patterns you see. How about you summarize this to your fellow teacher? I want you to turn to your left and tell your partner, or see, just ask them, tell them what you were thinking, okay? Okay, I see a lot of pointing and gesturing, but I only have 15 minutes or so. So does anyone want to offer kind of a couple of summaries here, what you took away from this variation, this particular set? Yes?
There are different names, there are different order of statements, white spaces in some, no white spaces in others, comments, and different strategies.
That's not fair, you already know what we did.
We're seeing a lot of either it's an iterative or if-then, you know, the two different strategies.
Yeah, so we start seeing, it's like, well, let's try to go, let me show you how we try to reduce and express, how we're gonna read those 7 without actually reading those 7, or all the thousands of them. Okay, we're gonna, actually I'm just gonna, okay. Here's the same set, okay, and we're gonna observe that these 3 are the exact same if you remove comments and formatting, okay? So I only need to read one of them. So I'm gonna read the first of those identical ones and put a little badge up above it saying that this represents 3. Another one, the one that happened to be below this in the original display, it's very similar, except it's got different variable names. It behaves the same way, okay, I would argue. Even though those statement orders are switched, it behaves the same way. So I only want to read one of them, okay? And then I don't want to randomly do the same thing as before, as randomly pick one of the 2 to read, because I might get stuck reading a solution that has variable names temp1, temp2, and temp3, right? I want to read a solution that has reasonable variable names. So I'm going to try to figure out, I'm going to let students vote for the most popular name for every variable. Okay, so you could call this passive crowdsourcing. Essentially, instead of normalizing variable names in the traditional way, where it's like var 0, var 1, var 2, okay, which really destroys readability, we're going to let the crowd say what's reasonable. And then we have another problem. Okay, so we're trying to normalize variable names, and yet we don't necessarily know, here's the 2 solutions again side by side. It's hard to tell, like, how do we, in an automated fashion, tell that the variable result on the left here is really the same, in some sense, as the variable res on the right? Okay. So, more generally, how do we tell if 2 students voted for the same variable name? If we're saying what's the most popular variable name for this variable, I have to be able to understand what it means to be the same variable in 2 different solutions, to have been given 2 different names. So the way that we decided to do it was by looking at the behavior of variables while executing these on the test cases that were used to verify their correctness. So for the base of 5 and an exponent of 3, you see here that for these 2 solutions, the variables they take on the same sequence of values. Okay, now whether they have the same name or don't, we can say that the bases in these 2 solutions are the same, the exponents in these 2 solutions are the same, and the res/result are the same. We'll just have to figure out what's the most common name given to a variable that goes from 1 to 5 to 25 to 125 on this test case, or all the others. Okay, so a variable that takes on the sequence of values shows up in quite a large proportion of solutions to this data set. Most common name is unsurprisingly results, but there's a lot of other ones too. Some are good, some are terrible. Okay, we're gonna just call this the results common variable. And likewise, you can do this for all the variables in solutions, just iteratively renaming them, essentially, to their most common name. Okay. To preserve the one-to-one mapping between a variable's name and its behavior, we do have to resolve certain variable name clashes, because when you start just kind of willy-nilly renaming variables, you might change the behavior of a program. We're very careful not to do that. We also want this name to have something. We're essentially embedding the dynamic behavior in some way into the static representation of these renamed, reformatted solutions. And so when you have two common variables that behave slightly differently, okay, if they have the same common name, we will take the less popular one and append a modifier, a subscript 2 or 3, just so that they are named distinctly. So this is the same set of solutions you've been looking at since the beginning, but now they're renamed with our kind of global namespace, so to speak. And we can see that these two, modulo statement order, their dynamic behavior, their variables are the same, they have the same set of statements, we only need to read one. And again, now we've incremented the little badge above it to indicate that it represents 5 solutions. And now we have our final set of 3 solutions that represented the original 7. That's how we're summarizing the variation in this set. And when you generalize that to 3,800 solutions, the most popular, we can have a single synthesized representative that represents 1,538. So it's not just the most popular solution we're interested in how they vary. So all the less popular stacks by order, okay, are shown here in the UI, in a separate column that can be scrolled, so you can horizontally align them with the most common, and we call out the ways in which the less common things are distinct from the most common solution. We do this also this is the hangman example I'm going to continue talking about. It's a string manipulation problem, okay? It was a helper function for the hangman game. This is another example that's going to come back. These are functions that compute the derivative to a polynomial represented as a list of coefficients. And this is taken from the most recent, we started working with the residential offering of the same course. So this is, even though they had only 200 students, we still see this kind of large stack and then all the different ways that people implemented a lab. So this is just to give you a sense that there's many different, we've run this on different kinds of solutions in introductory Python programming classes, and it runs very quickly. So this is linear in the number of solutions. It runs in under 15 minutes on this computer. It doesn't require a computing cluster like the earlier example from Stanford. And for the solutions that we had, correct solutions to these problems, we were able to, for the simplest problems, we had the most dramatic reduction in the number of solutions that you might have to quote unquote read all of them. Okay. As you get to the more complicated solutions, such as those that take compute the derivative, you get less of a reduction in the total number of synthesized solutions. But there is one thing you're still getting. You're getting normalization of variable names, so you can hopefully quickly jump between solutions without really having to kind of bring in a whole new set of variables into your mind. It's this notion of trying to reduce the cognitive load of skimming. And I want to point out that Stacy Turman and I, for her master's thesis, adapted this to normalize incorrect solutions as well. Okay, so you might say that, well, there's more kinds of interesting synthesized we can add more equivalence classes, okay? And we're going to let you do that, but in the UI. We're not going to do it for you at this point because we want you to be able to customize what you're paying attention to. If you didn't just give a lecture on times equals and what that means, then maybe you want to ignore this. Maybe you just want to rewrite all the instances once people didn't use it to be as if they did. So I'm just going to quickly demo what that looks like. Okay, so I'm going to open up the rewrite tab, and I'm going to say, well, I'm no longer teaching about syntactic sugar, so I want to ignore that source of variation in this data set. And I'm just going to re-render as if everyone used syntactic sugar. And now the largest stack has grown. It has accepted those that were earlier considered distinct, and we can see that the second most common solution is this alternative, this for loop method, and just a few stacks down, we can see that that needle in the haystack, these very few recursive solutions are now very obvious. They show up high in the list. So it's helping us find students who are solving things in unusual ways. We can also filter and see what common normalized lines are. Whoops, okay, so. Now, we have to verify whether or not we actually helped people. So we grabbed 12 participants who were typical, the typical kind of person who would be teaching an introductory Python programming class. We asked them to identify the 5 most frequent strategies used to solve problems in these data sets for each of the 3 that I've described previously. And for each strategy, they wrote a code example, like literally a snippet from the interface, comments about whether it was good or bad, why they thought it was noteworthy, and their confidence as to whether or not this was a common frequent strategy. We compared overcode to a control interface, where you essentially just dump all these thousands of solutions into a browser window with syntax formatting, and you allow the person to skim, search, use Control F. So the question is, does overcode give you an advantage over that? If you look at how many solutions they read, as in just ignoring the fact that certain solutions in overcode represent a whole stack, okay? Then you find that people actually scrolled more quickly through solutions when they were looking at the raw, for the simpler 2 data sets. And it wasn't until you get to the more complicated solutions that suddenly it was in the overcode condition, where solutions are normalized in some way, that they could read more. They did, presumably because of the cognitive load of looking at each new solution. If you give people credit for reading the whole stack when they read a single representative, then with the simpler, then we blow the control out of the water. And you can see that at the end of 15 minutes, with overcode, they're reading 64% of the 3,800 or so iter power solutions. They're reading 25% of the over 1,000 hangman solutions, and they're reading 14% of the comp-deriv. Okay, also, if we ask them for each of these, the control and overcode interface, whether or not they were able to develop a high-level view of students' understanding of misconceptions, then absolutely they recognize that they're getting this high-level view from overcode, not from a more standard method of looking at solutions. Okay, there's one aspect of variation that I've glossed over that's really important for one of the aspects of solution variation I already talked about, which is readability, right? Variable names make a huge difference. This is a snapshot of our original paper about overcode. I just want to point out, we essentially just ignored all that variation. We said, we're not going to look at it right now, but let's try to bring it back. Let's say, to enable you to understand all the different variable names that people used when solving it in this particular way. Now, we're saying, okay, for every synthesized solution representative, for every common variable in that stack, there's 3 different common variables in this particular one. We can see that the common variable characterized by behavior 1, 5, 25, 125 showed up in 3,000 of the 3,800 solutions. It was named result in 2,500 or so of those, named A in 20 of them. And maybe we had a Spanish student because they named, since sometimes solution names don't make sense in isolation, but as a set, we can see that as a set, this person used base, exponente, and resultado as their set of names in their program. Okay. So I'm going to call that system FUBAS. It was originally called temp, but that's a terrible name for a system. So we're going to come back to this soon to answer the question about personalized feedback. All right, so to summarize what we found out about how we can help people understand solution variation, overcode helps people read more complicated solutions and read more solutions. FUBAS is an example of how to expand hidden dimensions, right? So we collapse dimensions of variation to see some things, and we can kind of unhide them again. All right, moving on to feedback, okay? We take the same subjects and tasks, and we see see if they can cover our students with feedback. All right. Now, when the subjects were writing code snippets, and we were able to map that back to the numbers of solutions that those code snippets appeared in, to tell how relevant it was to how many solutions. So for the simpler problems, if you randomly selected snippets from the browser control condition, you could pretty much hit people. There wasn't that complicated a space. But once you were in the more complicated domain, like the computing of a derivative, suddenly, if you only were randomly commenting on things, you were talking to 10% of your students. If you used overcode, you could speak to 50% of your students. This just says that essentially people realized that this difference was there. Okay, so to answer our question about how to give feedback on solution variation at scale, overcode helps teachers write feedback that's more relevant to more students. All right. Personalized feedback. Can we actually personalize this feedback to our students? Does it even matter if we personalize it? Well, I would argue that personalization is a good thing. Bloom back in '84 established that one-on-one tutoring, where you can give personalized feedback, is a gold standard in terms of its educational outcomes. And good tutors, at least according to some experts who analyzed tutor behavior, found that tutors ask students to explain their thinking. It's not just about generating more and more explanations if they don't get it. It's asking them to self-explain. In fact, Chi in '94 showed that you could pretty much get the same learning outcomes of people if you just asked how and why, than if you started giving them more and more explanations from yourself. So getting students to actively engage and explain, and also to reveal content progressively, so you don't overwhelm students with something too hard or for them with something too easy. So I have, how do we give personalized feedback on solution variation? Well, we're going to focus on readability. We're going to focus within readability on variable names. So we're kind of narrowing this down to actually build a system. And in feedback, we're going to give feedback in the form of personalized learning, active learning exercises, which we're just going to call as shorthand quizzes, okay, on good and bad names. By variable names, it's a very basic form of documentation. Without modifying execution, you can indicate the type and purpose of an object. Critically, Professor Gutag, who's one of our introductory Python programming teachers, pointed out that introductory students mix themselves up through bad naming. If you look at these two snippets, right, I is idiomatic in the first example because it represents indices in an input array. And the second time, I is not okay because it's referring to the values in an array. I'm sorry if you're not native Python speakers, but I'm trying to narrate exactly what this means. So context, the role the variable plays in the program is critical to naming properly and not mixing yourself up. A here, not okay, it's too short even though it's the same length as I, because I don't know what it means. And result, it's okay. All right, anyway, I couldn't resist throwing in a Donald Knuth quote here. He says that compares a good programmer with an essayist who, with thesaurus in hand, chooses the name of variables carefully and explains what each variable means, right? So some people take their variable names very seriously. If I were in a one-on-one situation, which I can't be when I've got thousands of students, I'd probably be looking over people's shoulders and be like, oh man, remember that variable name lecture we had last week? Let's talk about our choices here, okay? Because but I can't do that, so how can I get as close as possible? Our feedback workflow was we had teachers annotate good and bad variable names using the foo-baz interface that unrolled variation and variable naming. We had them curate these quizzes, and then foo-baz analyzed student solutions and delivered personalized quizzes to everyone. Well, most people. So if you remember that table of names that we kind of ignored in the original publication, you can imagine a teacher going back to this and saying, oh, okay, well for the result common variable, result's fine, accum is too short, num is misleading or vague, right? And they can do that for each of these common variables, okay? And they can do that actually in the foo-baz interface, okay, just so they have the context in which they're appearing a little bit more clearly. And then the system starts tabulating. It's like, okay, for that common variable result, you think a, number, and out are misleading or vague, and result is okay. Do you want to add any other examples? right? Do you want to add any commentary to explain to students why you thought this way before you send this off to students? If a student submits some random piece of code, a new piece of code, new student in your class, or this might be an example from your existing code base, they may use their own variable names you've never commented on. But Fubaz will identify that they have an instance of the common variable result and an instance of the common variable I, and it will come back to them and say, hey, you may not remember what you named that, but let's talk about, what do you think of these variable names, right? These are names that your peers have chosen. And let's see if you agree with our teacher, or want to start a discussion with our teacher if you disagree, about whether or not these are appropriate. So the idea here is that you have thousands of solutions. The teacher spends 10 minutes, okay, labeling maybe 20 variable names. And that generates a few personalizable quizzes that students receive and can continue receiving ad infinitum with new students as long as you don't change the programming assignment itself. We just did one of our user studies on this system, brought in 10 teachers. We gave them the same data sets in Fubaz. We asked them to generate personalized quizzes. And in 4 to 11 minutes, they were able to label on average 20 out of the hundreds, nearly 1,000 in some cases, of unique variable names. Okay, and they could cover at least 75% of student solutions with at least one personalized variable name quiz. This is way more than just giving a lecture and then they're touching the topic again. So that's our response to the research question about personalized feedback on solution variation at scale. Finally, let's see if students can help us out here. It's hard to get personalized help in large classes. It was particularly hard having such long queues sometimes as a TA, helping late at night in the lab. When there's many different solutions, you may not have seen a solution before, but someone else in your class has. And so our key insight was that students who struggle and then critically succeed on implementing a particular solution or fixing a particular bug, they are your friends. And we need to more efficiently collect and distribute the hints that they write, because they earned the right to write. Them. I want to call out to a former group member of ours, Juho Kim, who established the idea of learner sourcing. And this is targeted learner sourcing. A slight spin on it where hint writers and receivers are not drawn from the general pool. They've earned an expertise to be a hint writer. So just to give you a few examples here, we've got students who are waiting in the lab queue for failing a particular test, and the teacher can model good debugging strategies, but doesn't know the answer. But there's another student who says, oh, we can connect them with, I just fixed that bug. I can not give you the answer, but I can write it for you. And this is complementary to Piazza, because this is from an introductory Python programming class at UCSB. Students have a hard time finding the answers in Piazza because students are not necessarily writing their questions and answers in a way that supports easy searching, right? So we established a workflow that helps with that. Secondly, if you want to improve solutions, you can have a student who submits something that works, and the teacher says, oh gosh, that's not the best way, that's not how I would have solved it, right? Let me connect you, or let the system automatically connect you with someone who did it a slightly better way, who can remind you of a principle you forgot when you wrote this. So students who fix bug X can offer hints for people still stuck on bug X, and students can compare, when they're done, compare their finished solutions to other solutions and write hints to help the worst of the two in each pairing. So it's like you have, you start off with a buggy solution, the system is presenting you with hints when you're stuck, saying essentially, someone else tripped here, they were failing that test case too, and they reflected on what they finally did to make it work, and they've written a hint for you. And finally, when you get a working solution, there can be hints left for people higher up on the hill of optimality, right, who can tell you. In practice, the workflow that we implemented for the computation structures class here at MIT looks a bit like this, where students are testing against the teacher's test cases over and over and over again. As soon as a bug turns from as soon as the test turns from red failed to green, they may have some insight, and they can add that insight if they want to index of debugging hints indexed by that test case that you're writing about. And then the second workflow, they submit a correct solution, and from our bank of previously submitted correct solutions, you get paired with a slightly worse one and a slightly better one. Okay? And the nice thing about this is that also students start to get the benefit of seeing the space of solutions, not just teachers. So if you're Carl, we did this for digital circuits, so it was fairly easy to map solutions onto this. This from worse to better, we just used the number of transistors. It was a simple enough circuit for that, but you can imagine generalizing this for other domains. So Carl's going to look at Bob and write a hint for students like Bob in the future, who might help them write something more like Carl. And likewise, Carl gets to see Donna's solution and is challenged to write a hint for someone like Carl in the future, who wants to write something better like Donna. So we evaluated this in an MIT Harvard design class with over 200 students over multiple semesters. We had a series of higher and higher fidelity web applications that implemented the self-reflection workflow. One of my hopes for the future is to automate the prompting of students. Right now, we had to rely on people's memories to remember that they just fix a bug, and they should reflect on it before they move on, and also kind of call out to someone and say, hey, this would be a good time to reflect. It was most successful when endorsed by staff, just unsurprising. And for the comparison workflow, we collected, as part of our required reflection activity at the end of a lab, where we automatically showed people these better and worse solutions from our bank, and we then collected those hints and gave them to 9 students in a 1-hour lab study the next semester later, and found that students could understand what the previous students had written, that this was a reasonable task, right? And that they, I think 6 out of the 9 did, in fact, in the space of an hour, rewrite their solutions to be substantially better. So, in response to this research question about collecting and distributing hints about solutions, given that there's so many different solutions, we've demonstrated as part of these targeted learner sourcing workflows that give students an opportunity to peer teach in a somewhat remote way. It gives them beginnings of awareness about alternative solutions, which I really hope that students do get when they walk out of an engineering class, and also it reduces the dependence on staff. Okay, so in summary, I've reflected on all these different explorations in the space of building systems for teachers and students, and I found that this general idea of clustering and visualizing solution variation in a human understandable way can really help teachers gain insights into student design choices, enhance their test cases, give personalized style feedback at scale, at least on variable names, and collect and distribute student-written hints in an effective way. So my contributions here are showing demonstrations of these particular capabilities in the form of systems we've evaluated and deployed. There's a lot of related work in this space that has come out while I was working on this thesis, and I actually had to spend like 3 weeks just reading all of it that had come out since my last publication on these things. What's different, AutoStyle, they wrote in their most recent paper, they were inspired by some of my earlier writing, and I was definitely inspired by some of theirs. But this explosion of research was really a product of the fact that we suddenly had millions or tens of thousands of people in the same massive programming classroom. Okay, now MOOCs may or may not stay at that size, but certainly programming education at scale will continue. And in fact, I hope to, at the conclusion of my PhD, start my postdoc at UC Berkeley working on personalized programming education, where they have 1,500 students in their introductory classes every semester. One thing that makes my work different is that if you're Douglas Adams fans, you'll get this. This is what we're building are these total perspective vortexes, okay, for programming teachers, and hopefully soon for students as well, where in a single interface you can see at the same time all the different ways that people solve the problem. Help you take advantage of that, make that insight that you get actionable. I'm and just a quick shout out to what I'm really excited about in the future. This is from last year when I teamed up with Bean Kim to try and cluster the clusters, if you will, okay? And so, there's now, instead of having 800 synthesized representatives, maybe you could have 5 Bayesian, use Bayesian inference to cluster those and allow people to explore more higher level themes that come out of the statistical regularity of our normalized code representatives. So with that, I'm going to, oh, this cannot be the same reason.
Really? That's less than an hour.
Okay.
That's like 45 minutes.
Well, can someone hit the laptop 1 button real quick? I'd love to acknowledge my co-authors. Well, I don't even need to see my slides to know who they are. My fellow co-authors on the Overcode paper in Tokai 15 were Rishabh Singh, who I'm so in debt, Jeremy Scott, who helped write the UI, and Rob, and oh gosh, under stress that I forget my co-authors' names. That's great. Here, I have them written here. And Philip Guo, who provided the initial code to help us log variable values over their execution. Our FluBAS work, which was published in WISC 2015, was done with Jeremy Scott again. Lila Fisher helped me run user studies, and Rob, again, helped me formulate and execute this. Finally, Erin Lin and Carrie Kai and Rob helped me with learner sourcing workflows, so we published that work in CSCW 2016. Could not have, especially, Carrie came in at the last minute, helped me analyze the hints that students were writing and see if they actually complied with certain patterns that we see in expert-written intelligent tutoring systems to see if that would be an appropriate future use, essentially crowdsourced intelligent tutoring systems. Maybe that would be a future thing. I really have to thank Stacy. She rewrote my implementation of Overcode, and she helped me adapt it to incorrect solutions and deploy for a new interface, which I unfortunately didn't have time to talk about, which helped people grade hundreds of residential student solutions using the normalized views this past spring. This is probably the 4th time I've acknowledged you, but I'm very grateful for you taking me on. For the UID group, for welcoming me to human-computer interaction. I came from robotics, and it was a really, really warm, friendly welcome. To my committee members who've been here, so Chris and I have been teaching together for many years. Leslie gave me advice starting when I was a sophomore in high school, so I came here as a nerdy high school student, and she has been a rock-solid source of perspective ever since. Shout out to MIT CSAIL and especially TIG, because throughout the years, as my comfort with computer science, I was originally an electrical engineer, and moving into computer science meant many visits to TIG, asking questions like, how does this work? And please help me set this up. And now hopefully I'm leaving this place having learned a lot from them. And finally, I'd like to thank the NSF, GRFP, NDSEG graduate fellowships, and the Amar Bose Teaching Fellowship, which helped fund a lot of this work so that I could do it alongside teaching or after my teaching responsibilities rather than at the same time. That was really critical. Finally, second to finally, I'd like to thank the Massachusetts wrestling community because they taught me a lot about life outside of academia. And my family, I can't list all the things that they have provided to help me finish. And finally, I'd like to thank the pugs. They have provided, and Victor, they have provided so much joy, especially in the last few years. Someone who may be here today has been leaving pug posters on my desk every once in a while, and it's very, very appreciated. So with that, I will take your questions.
Okay, maybe we can start with questions from the committee. Chris, I don't know if you want to go first, Chris?
Sure. Slide 58.
Okay. Getting down to the 70s. Yes.
There we go. Can you talk a little bit about why reading an actual raw example is different from reading a stat? There seems to be some difference.
Yeah. Well, my speculation, since we weren't really able to truly probe this difference, is that when you do normalized solutions, there's a little bit, it's not exactly what you're used to reading, right? We try to make it as close as possible, but there's subscripts in there, right? And these are crowdsourced names, so sometimes maybe I think when you're used to reading student code filled with comments and formatting differences, you might also just be like, yeah, and you just kind of scroll, like, I'm getting a general idea. So I think that people were more comfortable looking at messy student code and just kind of moving on and just scrolling. That's what I think that this was caused by.
It would seem to be harder to read unfamiliar, slightly messy code. So that intuition is wrong.
Okay. Well, I guess the reason I mentioned the fact that it might be harder to read is a certain kind of laxity, I think. Here they were not being asked to write down an assessment of every solution. They were just told to get a sense of common, themes in the code. And so if it's really hard to read each one, if there's no hope of like seeing each one after another and reading it in its entirety because it's normalized in some way, then I feel that my guess, again, speculation, that people were kind of just giving themselves a break and just letting them roll. Yes?
Could it also be that the overcode representatives are actually rather different from each other? Whereas
Oh.
in the control, you were tending to see kind of a whole run
Yes.
that
So-
basically looked the same.
So that was my guess too.
Oh, okay.
Okay.
All right.
But then it made me wonder if, I don't know what order you present the stacks in. Is it by,
It's the order of occurrence, right? So if you've got 1,000 solutions and 500 of them are essentially the same, right? Those 500 in the control are going to be interspersed throughout. And so it's like, oh yeah, that one again. Oh yeah, right? Whereas with the overcode, it's like, okay, you saw the first 500 in the first solution, right? Now on to the next. So okay, this is slightly different. Let me understand that. So yeah.
so then my question boils down to, if you think it would be better for productivity to actually, instead of displaying them in order of occurrence, once you've seen the most popular one, show one that's actually only slightly different, even though it
Yes, and
so
that
that
is,
would take advantage of the sort of coherency that maybe we saw in the control.
yes, that's exactly what Grover code does. So Grover code was overcode 2.0, but for rather than focusing on these edX lectures, because we had these live in-person staffs we could work with. They only had 200 some solutions for every example, but we would say, okay, well, for this set of solutions that behave the same way, here's the most common one, and here's the closest one to it, right? And we're going to show you the diff, and then you can move to the next one, and here's how it's different from that one, and yes.
Great. Maybe we can round robin here. Leslie, would you like to ask a question?
Well, sure. So first of all, can you hear me?
Yes.
Okay, good. So I guess being a machine learning sort of person, I was interested in some of the underlying clustering techniques. So some of your work, you clustered based on some syntactic properties of the program. And then in some later work, you clustered based on some sort of execution trace type properties.
Yes.
So I'm just curious if you could comment on those strategies and whether you thought about other representations.
Yeah, so I think what Leslie is commenting on is something I didn't focus on in the defense, but is in my thesis. These original overcode clusters were very much based on syntactic choices of students because I was interested in actually reading what students wrote in some meaningful way. The most recent work is where we apply these, we look at just the execution traces. No matter how that was generated with syntax, we say, look, the variables behave this way, okay, and we're going to cluster in variable behavior space. And the beauty of that is that now you don't have to explicitly say, hey, merge these two forms that are essentially one syntactic sugar of the other, right? That's taken care of for you. Now, the trick then, I guess, is explaining what that resulting cluster is in a human interpretable way. So rather than showing a single piece of code that represents a whole bunch, we have to say, maybe here's all the different distinct syntactic choices that resulted in this particular behavior that solved the problem in this way. So I definitely think it's the direction that I'm moving in. I don't think that the strategies I've written here to summarize syntactically groups of students will go away. I think that that's just going to get subsumed into more robust clustering methods that can also look beyond the syntax.
Yeah, I mean, basically, if anybody comes into my office and tells me that they're working on clustering, I always give them a bad time, because it's hard to know when you've done a good job, right?
Yes.
You say, well, look at these clusters, aren't they really interesting? And people say, oh, yeah, very good. But it seems to me that there are all kinds of different objective functions that you could apply to a clustering. And so it's interesting to think about, well, if what you want is inter-cluster readability or something, that's one thing. If
Right.
you want will predict the student's grade, that's a different thing. And
Right.
so
Right.
when you think about clustering and features and so on, it's interesting to think about what you're going to use those clusters for and whether these clusters are serving that purpose.
Absolutely. We have not looked into predicting grades, so now that we're working with grading teams, that's within the realm of possibility. I typically think of, predictive grading as being something that's kind of acting behind the scenes, as kind of that invisible helping hand, whereas a lot of what I focused here on was the objective of making you feel like you had read 1,000 solutions, even though you hadn't.
Good.
Great,
Yes.
let me ask a question. So all this work that you've shown us has been in Python, which is great because there's lots of